record, boop, share screen. Boop. Right, this shouldn't take too awful long. And then once I get through this, then you will today work on finishing the two from yesterday if you haven't already, and then the new one from today, and that'll be it. Easy peasy, right? So I put this one off. I remember that one day I said I was going to do it all, and I kind of like doing it separately, I've decided. So this one today is permutations. So I can't believe it's the 20th. Yeah. Wow. And so you'll remember when we talked about combinations that there was something I said about it that was pretty important. I don't know, maybe, I don't know, be weird if you remember, but do you remember what makes a combination a combination? Ah, good memory. With combinations, order doesn't matter. With permutations, order does matter. Good job. So if we look at something, a math problem, and it's just like we're just picking a group out of a group. Like I just want to pick, Mr. Disman comes in this room and says, hey, I need 3 students for a task. I would look at that as a simple math problem. I would say, well, there's 8 students. So we're doing 8C3 because order doesn't matter. Like he's not picking you in any certain order. However, it changes if now we're electing like a president, a vice president, and a secretary, right? Because like just saying, okay, the winners of the election are Shariah, Diedrich, and Micah. I would never be. That's not the point. The point is that that doesn't give us any order. Like maybe Micah's the class president and Diedrich's the vice president and Shariah is the secretary, or maybe Shariah is the president and Micah's the secretary. I don't know. So once we care about the order that things get picked in, then we have to switch our formula to something called permutations. We clear? Okay, so first off, let me give you the formula for this. And this one is NPR. And this is the one, if you have a really good memory, or well, maybe if you weren't here, you watched the video, whatever, I messed this up. And your calculator will do this, but you'll remember the first day I gave you the wrong formula. Does that ring any bells? Yeah. So that was the formula that I accidentally gave you, was the NPR. So the NPR formula is just like the NCR formula, but there's a factorial missing from the bottom. So if you want to know, if you have a group of n things and you're going to arrange them r things at a time, you would use NPR, which goes like this. The top is n factorial, and the bottom is n minus r factorial, and that is it. Done. Will there be, if I, think about it, like if I was going to do, like, let's go back to that 5 card example where we had A, B, C, D, E, and we were picking them out 3 at a time. If I switch it from combinations to permutations, will there be more or less? Tons more, right? Because if order matters, it's not enough for me just to say ABC is the same as ACB and BCA and BAC is CBA and CAB. Like those all get their own respect and recognition, right? So with permutations, you're always going to get more than with combinations because if order matters, you get a lot. We agree? Okay, so let's take a look at how we do this. And by the way, I've got some terribly bad news. I'm not holding out on you here. You cannot pull these from Pascal's triangle, okay? There is no magic triangle for this unless you wanted to like make one. But Pascal's triangle itself does not give these out, just so you know. But I will show you when you're ready. I offered it the other day. When you're ready to let me show you on your calculator how to do this, there's literally just a button for everything you need. So and yeah, let's practice. Let's say we have, well, let's go back to the example I did before, where we have those cards, where we had A, B, C, D, and E. And we're going to arrange them 3 at a time. So as soon as you see the word arrange, that's like your ding, like your green light to say permutation, baby, because I'm making arrangements. So we're going to take these and we're going to arrange them 3 at a time. Do you want to do this one manually? We could. Okay, you asked for it. So here it goes. First off, we need to consider every possible arrangement of just those 3 cards, A, B, and C. Settle in. Okay, this is going to take a few minutes. Now, don't move on to ABD or ABE or anything. I got a stick now right here in my sweet spot. How else could I arrange A, B, C? Yep. But again, in being kind of OCD, not necessarily in my everyday life, but in math, I feel like if I can be organized, I'm going to. I'm going to do the other arrangement that keeps A in the front spot. And then I'm ready to do the ones that start with B. Are there any others that start with A? No. Yeah, it's either A, B, C or A, C, B. Like there's no other way. So now I'm going to head to the ones that start with B. Which one could we do first? BCA is fine with me. And is there another one that starts with B? There is BAC. What about the ones that start with C? There is CAB, CAB, and there's, of course, kebab, CBA, right? Now, here's the thing is we just did 6, and that's just for the combination of A, B, and C. So if you pull out the combination of A, B, C, and then you start to arrange them into permutations, you realize, oh, snap. Like, whereas a couple days ago, ABC would have been one answer. Now we're going to have 6 times as many answers as before. And if you're a supremely strong math person, you see exactly why that's happening from the formula. There's a missing factorial that's causing this to happen. So, anyways, now we have to move on. You asked for it. The ones that have A and B and D. This will take a minute. So there's ABD and ADB. Okay, let's move on to B. There's bad and bada, and then there's dab and boo. Got it? You want to stay organized. I know I said that once before, but I really mean what I say. You'll go nuts if you try to just start picking one out of your gadushka, like, oh, I'm just gonna throw out ECB. Woohoo. Yeah, don't do that. Who's the next combination of numbers or letters tiles that I want to pick out? I want to stay with the theme of A and B. So if you go to CD, again, you're going way off to the end. I'm staying right close to the left. I'm asking myself, are there any other combinations of cards that have A and B? And there is. I've already used the A, B, C, the A, B, D. Now I need the A, B, E. So the good news is, like, once you find a combo, then you just start mooking around, and try to be organized. Again, if you haven't figured out my pattern by now, you know that next is going to be A, E, B. What's going to go next? B, E, A, and B, A, E. Very good. What's after that? E, A, B, and E, B, A. By the way, Aubrey, it's good to have you back. I like to say that earlier, but I kind of, you were busy in class, so glad you're back, kid. So those are all the combinations that start with A and B. And now we have to move on to A and C. I'm still trying to pack as many as I can that have A. Like A's like, don't forget to include me. Now, why would I not go back and backtrack to ACB? I've already done that. So that's why we work our way from left to right. You never have to backtrack if you're uptight. Be uptight about these. But the next one, as I progress from west to east, is ACD. I don't have any up here that are some arrangement of A, C, and D. So now I got to go down the whole list again. ACD, ADC, CDA, CAD, DAC, DCA. Still good? Are there any others that would include the letter A? Already got ACD. Good job. ACE. Ace Hardware. And then, of course, there's A, E, C, and then just, I'm telling you, be specific. Be uptight about it. CAE, CEA, EAC, and ECA. So I'm going to ask you this again. Are there any more that include the letter A? Yes. A, D, E. So now I have A, D, E. Remember, I gave you the option. You guys wanted to do this, and we're not even done yet.
How many more?
Not too many. The worst is almost over, I promise. Kind of. So A, D, E is good. And then we're going to keep A in the front slot, rearrange the D and the E. And then we're going to move D to the front slot. Ooh, there's the Drug Enforcement Agency or Administration, whatever that's called. And then there's finally E, A, D. I will ask you now again, are there any more that we have not included that start or include the letter A? I don't think so. And the reason we can say we feel good is because of how uptight organized we've been, just trudging like a snowplow our way from left to right. If you pull everything out as you go organized, then you just know when you've made it to the end, right? But we're not done, because now where do we need to go? We need to go to the ones that start with B, just in case you weren't having enough fun already. The first logical combination to me feels like it should be B, C, D. Let's just keep those three homies that are right uptight already together, huh? So now we got to do all 6 arrangements of this. BCD, BDC, CBD, CDB.
Sound like you're like speaking slowly.
DVC, and DCP. I know it's getting hard for me to keep saying these letters. Okay. So we have now done the combination of B, C, and D. Are there any others that would start with B and C? B, C, E. Basic computer examples. Biting chewy elephants. Oh, here, the next one is basic electronic components. The next one can be calibrating big engines. And then the next one can be chomping egg bites. And the next one is EBC, and I'm running out of creative juices. Anyone got a good one for EBC? Say it again. Early bird coffee. I love that one. And then ECB. Yeah. No. Are we done with ones that start with B? We did BCD. We did BCE. Gosh, have we done BDE yet? I guess we better do BDE.
I want to go to bed.
I would love to go to bed right now. And of course, after BDE is BED, bed. And then just be organized. Just alphabetically push your D to the front, do them both. Push your E to the front, do them both. I'm not an I told you so kind of guy, but you can only imagine how nightmarish this would be if you were all chaotic about it. You got 0 chance of getting through this, right? Like none. So we got D, then BE, then we got D, then EB, and then we got E, BD, and EDB. Are there any more that would start from left to right with the letter B? I don't think so. We got BC followed by D, BC, skip ahead to E, and then we got B, skip ahead to DE. There's only one group left. We made it. What is it? Correct. So now we need to do CDE.
I think there's no studio on there.
Commercial driver's license. DCE, EEC, EBC, and ECD. I got a little out of order there, but you get the idea. Holy smoked salmon. Woo! We made it. Now, let's count them up. And by count them, I mean, let's not be morons about this. How many are in each column? Okay, so let's just count columns and multiply by 6. I spy 1, 2, 3, 4, 5, 6, 7, 8. I count 10 columns, which by my math
60.
means there should be 60.
That's true.
Now, you don't ever want to do that again, I'm guessing. Okay, fair enough. Now, imagine if we had done it for like 7 cards. 4 at a time. Woo! So the flow is the same as it would have been in the last lesson. And this is the point in the lesson now where we apply the formula and have our little moment where we either go, oh, that's really neat, it matches, or we go, oh crap, it doesn't match. What did we forget to consider? So let's do this. So when we set this up as a formula problem, we're going to set it up as 5P3. Why 5? Because there were 5 letters. Why 3? Because we're doing 3 at a time. We're picking 3, A, B, C, D, B, E, A, C, whatever. We're picking them and arranging them 3 at a time. Hence the choice to do 5, group set, 3, little baby group set. And here we go. Based on the formula that I just popped up on the board about 9 minutes ago, what's going to go on the top of this answer? That. Don't forget the F word, 5 factorial. And what's going to go on the bottom? 2 factorial. Now, by now, you should be starting to commit some of these smaller ones to memory. Does anyone know, top of your head, quick, what's 5 factorial? It is 120.
Holy smokes.
And 2 factorial is, and what's 120 divided by 2? Jackpot. And that was a whale of a lot quicker than doing it by hand. I asked, do you guys want to list them all out? And you said yes. That's on recording.
Dalton said yes.
Okay, well, that's all I heard. I just figured Dalton speaks for the masses. If Dalton says yes, then I figure everyone's like, yeah, let's be on Team Dalton. Let's write this out.
Yeah, I'll probably reshoot that.
All right, we're not going to count them out by hand anymore. So this time, let's do this one. Let's say that there are 18 students running in a race. And we want to know how many different ways can they place first, second, and third. So again, just picture the situation. It's like field day, right? You got 18 little kids lined up across the starting line, and they're all going to go booking it down the field, assuming that they're all relatively comparable athletically. The question is this: how many different gold, silver, bronze finishes can there be? Does order matter? Yeah, of course it does, right? Coming in first is different than coming in second. We do not want to count this out by hand, I assure you. So what do we set it up as? You bet your butt. 18P3. What goes on top? 18 factorial. What goes on bottom? Nope. It's N minus R on bottom. What's 18 minus 3? So the bottom is 15 factorial. Good.
Let's divide it by together.
Now, when I write this out, you guys picked up on this real quick the first day. No way am I going to write out all the top and all the bottom. I'm going to write out this much, and then I'm going to stop. Why? Because everything that is about to go after 16, 15, 14, 13 is going to also then have to be written on the bottom, and then I'm just going to cancel them out. And now you just type this into a calculator, 18 times 17 times 16, which, so there are 4,896 different orderings that those students could place first, second, and third. Now, if this next 5 minutes goes well, I'd like you to give me some sort of a sign, because I'm about to try to blow your mind. And it's not going to probably work because I'm super tired, but here it goes. I'm going to show you a different way to do a problem like this. Are you ready? Okay. And I hope when I'm done that you can relate what I'm about to show you back to this. And you don't have to like fake it and be like, wow, Mr. Aaron, that's really cool. But I hope you do find it to be interesting how we can take different approaches to this. So here it goes. I'm going to draw the podium. Because why not? Because I'm such an artist. So I think the way it usually goes is like second place goes like here. The first place person is like up here in the middle. And then third place, because I watched this like Formula One. You guys ever watch those crazy Formula One drivers? Something like this. So the podium looks like this. So like first place will sit over, stand over. Oh, Sorry, my bad.
I was gonna say,
I knew that. I was just testing you.
oh,
So first place goes on the high one, of course. Second place goes here, and third place goes here. So all this set up for some very basic math questions. Stay with me now. So while the kids are running the race, ready? How many of them, how many possible kids are still in the running to finish first? All 18 are still alive. Now,
I hope so.
let's say Aiden crosses the finish line first and he's like, woo! There are still some kids running the race. How many of them are still eligible for second place? Dope. And finally, once Aiden has crossed in first place and Dalton has crossed in second place, there are still how many kids eligible for third place? And the counting principle says that if you ever want to know how many ways there are to do something, just find out the ways there are to do them all and multiply them together. 18 could be in first place, 17 in second place, 16 in third. And that should look familiar, right? Let's do this one. Let's say you walk into Miss Nolting's classroom and there are 19 students in it. And just for shiggles, you decide, I want to go in and take a picture of 5 students. Now, because I am, really into this photography stuff, I want to take every possible arrangement. What? What is your deal? Well, how come do you keep laughing at me? I know, because I can't say the other one. It's a dirty word and I can't say it on the video. Right? So we're going to do photographs of 5 people at a time, and we are going to do them in various arrangements, which means that order matters, which
How
means
did you just do it? No, not that.
arrangements, which means that order matters, which means we have to consider this as a permutation problem, correct? Now, here we go for the setup, and I don't want anyone to read me an answer yet, okay? I'm more interested right now, like mechanically in the setup. So this, we all agree, is 19 permutations 5 at a time. So 19p5, right? Picture it. You set down 5 chairs in Miss Nolting's room and say, okay, I want you, and you. And then you're like, well, let's rearrange you. You two switch. You two switch. You're going to do that for all 24 kids or all 19 kids in the room. So what goes on top? 19 factorial. What goes on bottom? It is correct. 14. You subtract them and then put that factorial on the bottom. How much of 19 factorial do I need to write out?
19.
Up to and through the 15, right? And then you stop. So 19, 18, 17, 16, 15. Yeah. So think about that. If you just walked into a relatively small class with 19 students and you wanted to take pictures of them 5 at a time, it would take, you would have to do 1,395,000 different photographs just to get 5 of them at a time. Got it?
How many years?
Yeah.
Well, interestingly enough, we're going to consider that here in our next example. It's one of my favorite examples. Are you ready? Okay, good. I'm going to take that as a yes.
Our silence.
What?
I said our silence has a yes.
So this time we're going to go into a larger situation. We're going to go into a more full classroom, like my, what is that, my 3rd hour class. I have 24 students. And let's say that we wanted to take photographs of them, but we wanted to do it 8 at a time. So
Excuse the interruption. We would like to have all wrestlers and band students to the Commons for Charlie Marie signing.
if you need to, sure, go ahead. Yep. Go do your thing. So We're going to set this up as a permutation problem. So because order matters, right? So this one will, I think, blow your mind a little bit. Are you ready? Why does that keep happening whenever someone goes out? Like you physically have to try to prop the door. Yeah, like it doesn't happen by accident. Thanks, Foxer. So here goes 24 P8. Oh, excuse me, not P8, P16. So how much of the
16.
24 minus 8? Oh, no, it's 24 P8. I was already into the formula. Gosh, I knew what I was doing. 24 P8. And then when we set it up, what's going to go on top? 24 factorial, and what's going to go on bottom? There you go. Yeah, sorry, I was getting my mental paths crossed. There we go. How much of the 24 factorial do we actually need?
24.
Good. So we're going to do 24, 23, 22, 21, 20, 19, 18. All right, I'm gonna work it out too here, kiddo. 24. So my calculator says a number that's pretty hilarious, and you might wonder what this means. So I'll show you what mine says. Mine says 2.965419072 E10. Does anyone know what E10 means? So if this ever happens to you, I've had people think this means like something weird. It's a scientific notation. So it means, hey, move the decimal 10 places to the right. So the number has gotten so big now that the calculator runs out of storage, not storage, but screen space. So if you take this decimal now and move it this many places to the right. So here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I need to add a 0. And now if I count these backwards, I put a comma here, a comma here, and a comma here, and that is 29 billion 654,190,720-ish different photographs that could be taken.
That's ridiculous.
So if you were going to arrange in a room with 24 kids, just a normal, come into my 3rd hour class and take a look around, just 24 kids. If we were going to put 8 chairs out in the hallway and say, okay, we're going to arrange 8 of you at a time in those chairs in every possible way, there would be almost 30 billion ways for us to do that. Now, someone asked the question, how long would that take? Let's figure this out. I think you'll appreciate
Well,
this.
how fast is our cameras on the
How fast do you think if I put 8 kids out there and said, okay, rearrange, go. How fast could 8 kids all rearrange themselves into a new one?
24.
Okay, that didn't go well. So how long does it take for kids to go from sitting like this to sitting like this? How long should one rearrangement take? Let's go with 5 seconds.
Yeah.
So if it's 5 seconds per arrangement and there's 60 seconds in a minute, then that means that you can do 12 rearrangements if you're very efficient every minute. Is that correct?
Yeah.
So if you can do 12 every minute, how many could you do in an hour? How many minutes are in an hour? So I would have to do 12 times 60, which means that if we're really fast and like we keep on, no potty breaks, no mess ups, if we're perfect, like robotically efficient, and every 5 seconds we can pick new seats, we could do that 720 times per hour, correct? How many hours are in a day? So multiply 720 by 24. I got 17,280. Is that correct? So that means we can arrange ourselves 17,280 different ways in a single day. How many days are there in a year? So why don't you take that 17,280 and multiply it by 365? So this means now that if we're really perfect and we never take potty breaks and we're like robots and we never have to stop to eat, we can rearrange ourselves 6 million 307,200 different ways or times every year. Now, here comes the issue. We're still not even close. If we spend one whole year doing nothing but rearranging ourselves 8 people at a time in a set of chairs, one whole year,
That's sort of
perfectly robotic, perfectly predictable every 5 seconds, we can get 6.3 million done in a year. Now, if I want to know how many years it's going to take, I need to take the total number of rearrangements and divide it by how many I can do per year. So let me do that for you real quick. I've always found this to be very interesting. The math does not lie.
I'm surprised Mr. Allen doesn't teach us.
What's numbers you provide?
Take the big white number, the one at the bottom of the TV, and divide that by the 6,307,200. And if I'm not mistaken, I'm pretty sure my calculator works okay. According to this, it would take around 4,701 years for those 24 people to arrange themselves in every possible ordered combination of 8.
No, but not everyone's going to be alive.
Medical.
Really, the purpose of this isn't to have some deep discussion about the fact that humans aren't going to be alive. The purpose of this is to try to open your eyes to just how amazingly big numbers can get and how quickly they can get that big. We're not talking about like an auditorium full of people here. We're talking about my 3rd hour class. You clear on that?
Mhm.
24 kids, if they wanted to arrange themselves 8 at a time for photographs, it would take them 4,701 years of doing nothing but that. It's pretty amazing, isn't it? If you don't think that's amazing, you're probably just not one of those people that's wired to think about math, because I think that is amazing. Nuts. So I'm going to hand out your last worksheet, and we can go through some if you want to, but I don't think you'll struggle too much. It's just you're going to use the NPR formula a lot. And by the way, if you have a TI-30 calculator, it'll do the NPR just right there for you. So allow me to show you that if you'd like. I don't mind. It's pretty cool.